the title of this talk is Pure Spinners for the Practical Physicist.
Oh, thank you. There was a remarkable progress recently in the field of integrability of n equals 4 Young Mills, which is equivalent to ADS5 process 5. But notice that we have now at least 3 candidates for worldsheet actions on the string. It is a Green-Schwarz action, it's a pure spinner action, and recently discovered Berkovits-Waffa action. So it's not very clear for me why one of these actions would be more integrable than others. And most likely what probably happens is that integrability appears only after you consider physical states in the string. Somehow you have to pass to BRST cohomology in the pure spinner language in order to get integrable structures. Or maybe there is some conformal field theory which is better than the others in this respect and which is integrable. So it would be very interesting to address this question. And one way of addressing this question would be, well, a good feature of pure spinner formalism is that you can expand around flat space and observe things order by order in perturbation theory. So in principle, we could just start expanding vertex operators, for example, in pure spinner and in orders of 1 over radius of ADS space, and at each order get some integrable structures. And what I'm going to talk about, and BRST complex, so how these things interact. So what I'm going to talk about is kind of step in this direction. We will mostly do perturbative expansion of the transfer matrix. Yeah. So what is transfer matrix is basically if you want to calculate it's useful when you want to calculate a correlation function of 2, for example, operators d plus x at 2 different points on the string worldsheet. So these things live in the tangent space to the target space. So when you consider d plus x at point A and B, you cannot just multiply them because they live in different spaces, so we have to parallel transport. Obviously, you can just use Levi-Civita connection to do parallel transport, but this is not very good. Levi-Civita coming from just Christoffel symbols coming from ADS space. But first of all, it will depend on the path from A to B, and it's somewhat unnatural operation because it's not a flat connection. So instead, in the integrable systems, we should use transfer matrix, which is a natural way of defining such operators. Transfer matrix, as I said, is a parallel transport type of object, and it's defined as we draw a contour from point A to point B, and then calculate path ordered exponential of certain integral of certain current J, which depends on the complex number Z, which is called spectral parameter, and then this thing would be independent of the choice of the contour. Classically, in the classical theory. So we have a family of parallel transport operations which depends on complex number, spectral parameter. So what happens quantum mechanically? Actually, we don't know, but we conjecture, well, it's natural to conjecture, first of all, that so we conjecture that there are no, in this object, that it makes sense quantum mechanically, and when you define it, you have immediately some linear divergences, but no log divergences, similarly to Wilson loop in QCD, I guess. Sorry, yeah, indeed. So no log divergences. And after you subtract, so this was demonstrated at one loop in our paper with Sakura, Schaffer, Nameki. After you subtract linear divergences, you get it, the regularized functional is independent of the choice of the contour. At one loop, we have some work in progress with Sakura and Valentina Puletti, which seems to be pointing in this direction. So notice, however, that if you consider this transfer matrix, then it will, according to our conjecture, it will be independent of the choice of the path, but except for it will depend on the tangent directions at the endpoints. In other words, it's also logarithmic divergences. There are no logarithmic divergences in the bulk, but near the endpoint there will be diagrams associated to the endpoint. So endpoints will acquire both anomalous dimension and anomalous spin. And in particular, this function would depend on this angle here. So let me describe simple technical things. So most important object is this algebra PSU224, and I prefer to think of this algebra in terms of symmetries of string theory in ADS5 cross S5. So we have bosonic part are killing vectors on ADS5 cross S5, and fermionic part are supersymmetries. So to understand the Z4 grading, the Z4 grading is important. To understand the Z4 grading, we pick a marked point in ADS5 cross S5. Imagine this, the blackboard is ADS5 cross S5, so we pick a point. This is a point. So G naught, so G has Z4 grading, G naught plus G1 plus G2 plus G3. G naught is rotations around this point. Part of the symmetry group's acts as rotations, or Lorentz transformations, they just preserve this point. G2 acts as shifts. These are kind of momenta, the shifts. And these things are fermionic supersymmetries, which come from left and right sector of the superstring. And because it's type 2b, they have the same chirality, actually. So these guys have the same chirality. So the indices reflect the fact that they're kind of tangent space object to the 10-dimensional space in a given point of ADS cross sphere. The transfer matrix is defined using this twisted loop algebra of PSU224. And twisted loop algebra is very similar to this algebra generated by this T's, except for you put additional integer index. So the lower indices are, this algebraic index is the same as on T's, as generators of PSU, but the upper index is an integer. And when you commute, you have to sum upper indices. So that's what twisted loop algebra is. And it's called twisted because the upper index modulo 4 correlates with whether it's with the Z4 grade of the lower index. If you, there are some currents, I will explain this current. So J naught, J1, J2, J3, and N is constructed from pure spinors. So this currents, if you construct this thing, then this would be independent of the choice of the contour, this integral. It's a flat connection. And most important thing is the evaluation representation of this loop algebra, where you pick a spectral parameter Z and construct a representation of loop algebra from finite dimensional representation. We usually think of it as actually this T acting in an adjoint representation. If nothing else said, then we think that T is. So we will consider mostly evaluation representations of adjoint representation. So the basic object I would love to would like to consider is Wilson line with operator insertion. Infinite Wilson line is a very important object. For example, it generates conserved charges and local conserved charges. But to make some fun out of it, we better insert some operators and see what happens after we insert. You could call them impurities, if you like, the word. So eventually, we would like to study the networks of this object. So we would like to know how to intersect two Wilson lines, or if you take two Wilson lines, for example, one pure and the other with one impurity, then we want to understand what happens when you flip them, when you exchange the raw upper line with lower one. What happens to this insertion? And so this type of question. So this is the plan. So first, it's an introduction. I briefly speak about log divergences in one loop, and then briefly about the algebra of transfer matrices with impurities. So this is the worldsheet pure spinor action. It's defined in terms of this cassette space. So in our notation, the denominator acts from the left. The denominator is identified with G naught in terms of Z4 grading. So it acts from the left. So J's are constructed in terms of G. Here is the action, and N plus are constructed from and minus from the pure spinor ghosts. So Valillo demonstrated one loop conformal invariance of this action. There are general arguments for finiteness and BRST invariance. We will work with this action from the point of view we expand it around flat space. So as I said, we picked one particular point in ADS space. And associated, so we picked a marked point in ADS space, and after we picked a marked point, there is a special choice of gauge. In other words, a special choice of lift of ADS from the cassette space to the numerator group. It is given by this formula. Thetas and x becomes coordinates on super ADS space, this marked point, and the action, if you expand it now in this x and theta, becomes this. So this is a well-defined expansion around flat space. For example, we can, even on the classical level, we can expand transfer matrix and get something like this. From point A to point B, this is 1 over R term, and so on. This is a spectral parameter. Nice expressions, actually. Technically, it's important to understand that the currents J plus minus, even though they're defined like this, and G actually, the global symmetries acts as constant shift on the right, multiplication by constant group elements from the right on G. But these currents, after we fix the gauge, because you need a compensating gauge transformation, they are not invariant under global symmetries, but invariant up to compensating gauge transformation. So in the gauge fixed action, if you want it to be global invariance, you have to say that pure spinors also transform under global transformations according to this. For example, under shifts, there are shifts. Remember those elements of G2, which just shift the marked points. They act non-linearly on X, like this, and so you need to do compensating transformation also on the pure ghosts. So the one loop log divergences of the transfer matrix arise from diagrams, at one loop level with one propagator. So there's a Wilson line and you draw one propagator. And so they have this form. The power of R is twice less than power of X or theta. And there are various sources for them. There are internal divergences of currents because it's interacting theory, because currents are composite operators. And also because you have a multiple integral of currents when you expand in powers of 1 over R. Like I did here, you have multiple integrals and there will be collisions in these integrals, which also lead to logarithmic divergences. So, well, for example, just example of renormalization of the current, there is this vertex in the action, and this vertex would lead to a renorm group acting on G naught, mixing it with a pure spinor current. And so you get this expression, which should cancel against something according to our calculation, which it does. Also, the double collision. So we have a double integral like this. For example, we expand, we get the term with J1 plus. And there is logarithmic divergence here proportional obviously to Z to the minus 6. And C odd is some kind of Casimir operator acting on D plus X. So there is a log divergence, but it will cancel. It will cancel against what? It will cancel against triple collision. So the simplest way to understand triple collisions is to look again at the transfer matrix in the finite interval. So transfer matrix from A to B. And if you expand it, it's right at the order R minus 2, you get this term, which is log divergence. There is a linear divergence proportional to length of the contour. There is this log divergence. The right way of thinking about this log divergence is to say that it's either endpoint anomalous dimension here. It's shared between, it's split by 1/2 between these two endpoints. And it arises from double collisions of dx with the endpoint. Similarly, if you expand so to the third order of 1 over R, then there will be triple collisions of D plus X, D plus X, D plus X, leading to this contribution to the log divergence, and it happily cancels with that thing which I shown before, with double cancels, triple, so it cancels. So to demonstrate all these cancellations, you need to know short distance singularities of the products of currents, and they were calculated by Valentino Puletti. And there are various interesting effects. For example, the double collision of two chiral integrals can mix under a norm group with the anti-chiral integrals. It's quite interesting paper. So we use the contour splitting regularization. For example, the product of two x's and dx is understood as you split along the contour. And because you split along the contour, epsilon is rather a 2 vector. So it turns out that log divergence is proportional to log epsilon plus, cancels separately from log epsilon minus, and this is independent of the choice of the shape of the contour, which is actually work in progress. So I now want to go to the second part, which is studying the product of two Wilson line and exchange relation between the product of Wilson line. So what we will do is we consider two Wilson line, two transfer matrices corresponding to two different contours, and then consider the limit when the contours approach each other. At the order, this is now, we consider one propagator. So we draw one propagator from upper contour to lower contour. Unlike the calculation of log divergences, here it's kind of a tree diagram with one propagator. So this is actually equivalent to computing the Poisson brackets, essentially classical calculation. And there was huge literature on Poisson brackets, and in particular, perhaps the last paper of Clousson, the most recent one, has some observations similar to what I will discuss. So what I'm going to do and what I'm interested in is defining the transfer matrix in the tensor product of two representations, ρ1 and ρ2. For example, two different evaluation representations. Well, the way I define the transfer matrix as a p exponential integral j contracted with e, I can just substitute for e just e times 1 plus 1 times e, just e in the tensor product, the action of the generator in the tensor product. And this is one definition. But on the other hand, I can just take two Wilson lines approaching each other. And classically, this will give the same definition because of these identities. Just the product of matrices is the same as matrix in the tensor product. But in the quantum correlation functions, we have to consider contractions. And there is a difference between these two definitions because, for example, because of the simple pole in the product of currents. And the difference is basically can be understood as two ways of defining the integral dw of dw. On the left-hand side, you calculate what's a contour like this, and on the right-hand side, you calculate essentially principal value. So there is a difference between these two definitions, and the question is, how do we think about this difference? This can be thought of as deforming the coproduct. So at least in this toy example, it's not trivial that it can be interpreted this way, but in this toy example, the difference between two ways of definition of the transfer matrix can be understood as substituting instead of the usual tensor product, this tensor product. What happens for string in ADS 5 crosses 5? So one possibility would be that these two objects are just different, essentially different, but this is probably not true. Another possibility is that we should consider the deformed coproduct on the loop algebra. And this also has some ramifications. First of all, it's possible that the proper definition of transfer matrix requires not just loop algebra, but some deformed loop algebra. And therefore, the use of standard coproduct would be inadequate because the deformed algebra would require deformed coproduct. Usual coproduct just would not work. So the right-hand side would be wrong. The left-hand side would automatically give the right result. The other possibility in principle that the algebra of generators is the usual loop algebra, but maybe there is non-standard coproduct. I don't know a theorem which would forbid non-standard coproduct. It's also possible that coproduct defined by this, by the left definition is different from the standard coproduct by conjugation, and that's what happens at one loop. Sorry, that's what happens at the first order in 1 over R. So it turns out that there is some field-dependent R matrix, which we will call R hat. Hat means that it's field-dependent, and it has this form. And with this dependence of two spectral parameters. And so this is this. It has this constant piece plus higher order powers of x and theta, and the first correction to the constant piece, field-independent piece, is this linear in x and theta. And the simplest way to think of this object is if you take two finite interval, you take two Wilson lines, you flip them. It's the same as this is equal to the flipped Wilson line, but conjugated by 1 plus r. So this object allows, in principle, to consider also the crossing of two Wilson lines. It's not very clear how to cross two Wilson lines because there are all kinds of divergences here. So, and we want the definition to be such that it's independent of the crossing point. And one way of doing it would be to first fuse this one definition, which is in terms of product, into the principal value definition, and then unfuse in the opposite direction. It's not clear for us whether this would be true or not. We just didn't finish the analysis of this crossing. So most likely, I think that the order of crossing would be different. So this diagram would not be correct. Even more interesting than crossing is looking at what happens when you consider various insertions in the Wilson line. So let me first say general stuff about insertions. So we can insert operator, and we usually want this thing to be gauge invariant with respect to G naught, which is denominator group. So if you take the representation after insertion can change. So you have Wilson line with representation rho, which is flipped into Wilson line of representation rho prime. And then for this to be gauge invariant, then O should transform into this representation of the gauge group, to be gauge invariant. For example, we can just insert J2 plus here because, so I'm using here add means that I'm using the evaluation of the adjoint representation. So I'm just inserting J2 plus here, and this would be gauge invariant. Or one of these would also, and it has engineering dimension 1, 0. So it corresponds to geometrically to D plus X or D plus theta, something like that. One particularly simple case is when we insert O equals 1, just 1, but change the spectral parameter. We will call it the switch of spectral parameter. This is gauge invariant because evaluation representation if you restrict it on G naught, which is a finite dimensional, just S of O1 cross S of 5, it will be independent of the spectral parameter. So from the point of view of gauge group, this representation is equal to this representation. So this thing is gauge invariant. Or we could insert, for example, a partial Casimir, something which is invariant on the gauge group. This thing is invariant on the gauge group because this combination of fermionic spinor generators is invariant on the rotations of tangent space. Or we could insert pure spinor, which transform on the gauge group, so it would compensate for, well, we could insert pure spinor also. So there is a class of operators here. Apparently, this class of spectral parameter switching operators is closed under BRST action, I think. Well, we will need also a notion of split operator. Sometimes when we take two Wilson lines approaching each other, it may happen that you need operators which consist of the product of two insertions on the upper line and on the lower line. And separately, it's not gauge invariant, but the product is gauge invariant because the product like this would be gauge invariant because at least in the limit when there are multiple subtleties here because you need a parallel transport here. But the subtleties at the first order of perturbation theory would not matter. You can consider fusing two Wilson lines with insertion and without insertion and get so the operators, the insertions there is a natural transformation G plus which acts from operators in the tensor product of two representations to tensor product of four representations. Or you could, if you take a split operator, you could exchange upper line with lower line and get some R, the exchange operator, the exchange transformation acting on this operator. And I want to consider an interesting example, which is exchange of switch operator. So let us take a Wilson line with insertion of switch operator, which so you have spectral parameter Z in, and here it turns into Z out, and this thing is gauge invariant. This bar just means a unit operator, but you flip the spectral parameter. And then I want to flip this. And this is the same as, this is equal to this, where you multiply by this object, which is 1 minus R plus of evaluated on Z out up the sorry, the up instead of the up should stand z1, and the down is z2. So you evaluate on z out z plus evaluate on z in z, such object. And so here is explicit expression for this R plus, and it is simpler, much simpler than what we had for this simple exchange of. Remember, I discussed exchange of two Wilson lines in finite intervals, and they had the dynamical, the field-dependent R matrix. 1 plus R hat, it was field-dependent. Here it is field-independent. So it's related to, this R plus is related to the leading field-independent term in R hat by adding to it something called S. The notations are due to Maillet. It's slightly unfortunate because it resembles S matrix. However, this S matrix is not S matrix. We call it stop matrix. And why we call it stop matrix? Because this matrix appears from the diagrams which are localized near impurity. So you have various integrations here. But when integration contour hits this impurity, there are additional diagrams because some integrations stop here. And these additional diagrams are encoded into this S. So you have to, when you flip, you have to insert 1 plus R plus here and 1 minus R plus here. And if you flip in the opposite direction, you have to insert R minus. And why it happens? Because R, the thing with R is the same, because the thing of R comes from the bulk of the product of two Wilson lines. It enters in the definition of the modified coproduct. So it's universal in these diagrams. But S comes from diagrams which know about impurity. So you have to tell whether impurity was on the lower line or on the upper line before the switch. And therefore, this S just sums these diagrams which exist because of the impurity. So there is an issue of sometimes the R and S matrix are dynamical, which means field dependent. And sometimes they are C numbers, field independent. And for example, if we just, as I said, if we just exchange two Wilson lines with endpoints, then we get field dependent. Why? Because this thing was not gauge invariant. It's not very bad that it is not gauge invariant, because we work in the gauge fixed formalism. Remember, we have this gauge G equals E theta EX. So once we fix the gauge, we can just consider this operator, the fact that it's not gauge invariant. We just define it in the fixed gauge. But it will not be, because of the compensating transformation, it will not be invariant under global symmetries. And this explains why the R matrix which appears here is dynamical. While this operator, in the intersection, I think it will be also, we did not think hard enough about it, but it will probably be also dynamical, actually. If you consider just exchanging the diagram with endpoint, it will also be field-dependent operation here. But in the switch operator, because the thing was gauge independent or independent, it was gauge invariant or invariant under global symmetries, then these matrices which appearing here will be just C number matrices. They will not depend on fields. This is because just suppose that when we do the switch exchange, suppose that this operation here, this matrix, was dependent on X or theta, then it would contradict invariance under the global symmetry, because global symmetry involves because the global symmetry, there is a symmetry under shift which acts as X goes to X plus Xi plus higher corrections. I think 1/2 X Xi, something like this, plus etc. It's good if you cannot see it because I forgot the coefficient. The leading term would invalidate the possibility of having terms depending on X. While if O was not gauge invariant, then the global symmetry would involve compensating gauge transformation coming from the bulk of the Wilson line. So you would have X Xi which this was d of x psi, so this would propagate to the end point, and then this x would contract with something, and this would cancel the variation of terms like this under the shift. It's kind of now we will discuss the consistency condition which arise from this picture, from the exchange of the switch. So the consistency conditions, I consider 3 infinite Wilson lines, absolutely infinite. And I put a switch operator on the upper Wilson line. Then I flip. As usual, I compare 1 to 3 to 1, 3 to 3, 1, 3 to 1 with 1 to 3, 1, 3 2. There are 2 ways of doing exchanging 1 and 3. So when I flip 1 and 2, this is 1 plus R plus and 1 minus R plus, which appeared just because this is the exchange matrix for the simplest impurity. Now I want to flip 1 and 3 now, and something unpleasant happens because when I flip 1 and 3, the endpoints of this is a split operator. It has T here and T here, roughly speaking. So this endpoint is also impurity. So now on line 1, you have 3 impurities. And when you switch it with 3, each one gets dressed by 1 plus R, 1 minus R. This is the original switch operator, but also endpoints. And this quickly becomes nightmarish because you want now to exchange 2 and 3, and what you get is something like this. Here, the impurity was on the lower line, and it was going up, so I have to use R minus instead of R plus, and R minus is denoted by a red arrow. So the other way of doing it is a little simpler. If you first switch 2 and 3, nothing happens, because those are infinite Wilson lines. Infinite Wilson lines commute. Now you switch 1 and 3, and you finally switch. And so you have to compare this with this. And it results in a consistency condition. And consistency condition is this funny expression, which is similar to what Maillet had with R minus. One of these R's is R minus, and 5 others are R pluses. And now, because we have issue with gauge invariance, we do not require this to be 0, but we have to require that this commutes with switch on 1 and nothing on 2 and 3. And how it works, actually, it works like this. If you calculate this thing, you see that it's equal to T no. It's a complicated expression. One thing it's polynomial in Z, but also another thing is that on line 1 is always T naught, the generator of G naught. So it will always commute, because this was gauge invariant commuting with G naught. So it will commute with, so this would be 0. The commutator would be 0. This thing is separately not 0, but it can be thought of as a gauge transformation. And this is a gauge invariant object, and that's how it is 0. So we see that we have interesting generalization of Maillet equation, which takes into account gauge invariance. And unfortunately, I have to stop here, not just because of time, but because it is work in progress, and we don't have much more to say. But let me reiterate that we have a remarkable progress in, in general in the field, there is a remarkable progress in the effective degrees of freedom, which are giant magnons. And so we studied giant magnons in the light cone gauge fixed approach. And my dream is to say something interesting about microscopic degrees of freedom, not about giant magnons, but to translate the statement about giant magnons to a statement about axes, thetas, and lambdas. Something about, because giant magnons, you don't see them immediately in the string action, and moreover, you have to go to the light cone probably to properly study them. But yeah, well, okay. But you have to fix the gauge somehow to study them. And my feeling is that by the time you discuss giant magnons, you kind of already done lots of integration in a way. So it's effective degrees of freedom, although they contain the same information, of course, as string in terms of physical sector. but they, in a sense, effective degrees of freedom. So the pure spinor approach has a useful property of having nice perturbative expansions around the flat space. And perhaps in this perturbative expansion, we could see some precursors of integrable properties of these giant magnons. Perhaps we could see some manifestation of integrability. It is not clear for me whether the theory will be integrable or not, but something should survive. Something should survive relaxing the physical condition. So we have seen that on the classical level we got a rich algebraic structure when we consider the algebra of Wilson lines with certain insertions. But it's important to understand how this algebraic structure involves QBRST. This is work in progress. And of course, it is also important how to understand whether we can guess quantum analogs, quantum generalization of this story. We have some hints about how to generalize this equation to from one loop to sorry, by quantum I mean higher loops, how higher orders of perturbation theory. So we understand more or less what happens at first order of perturbation theory, but how to read some high order of perturbation theory in these structures of exchange algebra. We have some hints, but it's very much in progress, so cannot talk about it at all. Thank you very much.
If you would do the same computation for DS3 cross S3 in theory, what would be different?
Well, cross T4. Well, I expect the same result, I think, but I haven't done it.
No difference at all?
Well, concrete formulas would be different, but it depends on something would be different. I think I will still have finite transfer matrix.
So you computed this R plus, S plus or minus.
Yeah. These things are essentially classical. So ADS3 cross S3, ADS5 cross S5, you should get similar structures. You can go to the sector. Even in ADS5 cross S5. Well, I expect we have the same. I expect we have the same structures.
We're gonna have some